Bismillahirrahmanirrahim. Assalamualaikum and hello to everyone. A very good morning. Uh, as you all know that your course is divided into three major parts. And we are right now covering the first part, which is about the advanced concrete technology. We have covered some of the topics, and the topic for the day is the concrete durability. Uh, uh, I think uh, if time permits, we will be covering the different concrete durability related mechanisms, and we will be discussing the multi-silica reaction in depth today, and maybe the freezing and thawing mechanism in our next session or presentation. So we are going to start with the concrete durability. Remember that this is one of those topics that bridges the gap between theoretical material science and the real world structural engineering practice. Before we dive in, I want you to think about something for a moment. Uh, 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 so think about that. Why do we spend so much time and money repairing concrete structures that were built to last 50 to 100 years? So the answer almost always comes back to durability or the lack of it. Today we will walk through the key deterioration mechanisms with a particular focus on alkali-silica reaction and freezing and thawing damage. We will see that if we are able to cover freezing and thawing damage, but I will be trying to limit my today's presentation to only alkali-silica reaction and maybe the freezing and thawing in some next session. So these two mechanisms, alkali-silica reaction and freezing and thawing, are two of the most prevalent and costly problems in practice. All of our content is anchored in three core ACI documents, ACI 318, ACI 201, and ACI 221, as well as the two most widely used textbook books in the field, Mehta and Montero, and A.M. Neville's book of properties of concrete. So let's get started. Here is an overview of everything we will cover today. We have 12 major topics organized into roughly four thematic blocks. We begin with the fundamentals, what durability means and what controls it. Then we move into specific deterioration mechanisms, starting with alkali-silica reaction and freeze-thaw, which get the most of attention. After that, we cover sulfate attack, chloride corrosion, carbonation, and abrasion. The second half of the lecture focuses on what we actually do about these problems. Mix design, concrete cover, curing, construction quality. We finish with a testing methods overview and a full ACI reference card. Please note that you don't need to memorize this structure now. Just keep in the back of your mind as we go, so you can see where each topic fits into the bigger picture. Let's start with the definition. ACI 201 defines durability as, and I am quoting directly here, the ability of concrete to resist weathering action, chemical attack, abrasion, and other conditions of service while maintaining its desired engineering properties. Please read that definition carefully. Notice it says resist. Durability is not about being indestructible. It's about resistance over time under the specific conditions the structure will experience. A bridge deck in Nawab Shah, for example, exposed to intense summer heat has very different durability requirements than a marine pier in Karachi harbor exposed to chloride-laden seawater. Now, why does durability matter? Primarily for three reasons. The first reason is structural safety. Deterioration doesn't just look bad, it reduces load carrying capacity. Corroding rebar, for example, expands and cracks the concrete cover, and that crack propagation can compromise shear capacity and flexural strength of the structure members. The second reason is economics. Mehta and Montero, in their 2014 textbook, report that in industrialized nations, approximately 40% of all construction industry resources go not into building new structures, but into repairing and rehabilitating existing ones. This is an enormous inefficiency, much of which is traceable to poor durability design at the outset. The third reason is the sustainability. Every ton of Portland cement produced releases approximately 0.8 to 0.9 tons of CO2. If we replace a deteriorated structure prematurely, we are spending that carbon budget all over again. Durable concrete is therefore sustainable concrete. Now, what actually controls durability? There are six fundamental factors, and I want you to understand each one physically, not just memorize them. The first and most important is the water to cement ratio or water cement ratio. This is the single most influential parameter in concrete technology. A lower water cement ratio produces a denser, less permeable cement paste. ACA 318 restricts water cement ratio to 0.4 for the most severe freeze-thaw and sulfate exposure classes and 0.45 for moderate ones. We'll see exactly why in a few moments when we look at permeability data. Second is cement type and content. Different cement types have different tricalcium aluminate contents, which directly affect resistance to sulfate attack and chloride penetration. Higher cement content also improves density, but only if the water cement ratio is maintained. Third is aggregate quality. Remember, aggregates occupy about 70% of the volume of concrete, so they matter enormously. Reactive aggregates, I mean those containing amorphous silica, can trigger alkali silica reaction. Porous or weak aggregates increase overall permeability. Fourth is concrete cover. American Concrete Institute table 20.6.1.3 of ACI 318 specifies minimum cover of 38 to 75 millimeter depending on exposure conditions. Remember, cover is the first physical barrier protecting embedded steel. If the cover is inadequate or cracked, every other durability measure is undermined. Fifth is curing. This is probably the most neglected factor on construction sites. ACI 308 requires a minimum of 7 days of moist curing. Inadequate curing leaves large interconnected capillary pores in the paste. Neville's data shows permeability can be 2 to 3 times higher in poorly cured concrete versus properly cured concrete even at same water cement ratio. Sixth is construction practice, proper compaction, avoiding over finishing, controlling placement temperature. All of these affect the microstructure of the final concrete. Okay, permeability, the root cause of deterioration. This is probably the most important conceptual slide in the entire lecture, so please pay close attention. Mehta and Montero write, and this is a quote I want you to remember, that the deterioration of concrete is largely function of the ease with which fluids can enter and move through the concrete. In other words, almost every durability problem is ultimately a transport problem. Aggressive agents, chlorides, sulfates, CO2, water need to physically migrate into the concrete to cause damage. If we can slow or block that migration, we can dramatically extend service life. So, what controls transport? The pore structure of the hardened cement paste. Look at the bar chart on this slide. This is based on the classic work of T.C. Powers and colleagues from 1954. At water cement ratio of 0.4, we assign a relative permeability of 1, which is our baseline. If we increase the water cement ratio to 0.5, permeability increases 9-fold. At 0.6, it is 70 times the baseline. At 0.7, which was common in older construction, it's 300 times more permeable. Those are not small differences. That's the difference between a structure that lasts a century and one that starts deteriorating within a decade. Now, there are three types of pores in hardened cement paste worth knowing. Capillary pores form when there is more water present than is needed for hydration. So capillary pores form when there is more water present than is needed for hydration. That is when water cement ratio exceeds about 0.38. These are large pores, typically 10 nanometers to several micrometers, and they are the primary transport pathways. Gel pores are much smaller, around 1 to 5 nanometers, and are intrinsic to calcium silicate hydrate gel microstructure. They don't contribute significantly to permeability but do affect shrinkage behavior. The interfacial transition zone, or ITZ, is a 20 to 40 micrometer thick zone around aggregate particles that is more porous than the bulk paste. It's the weakest link in the concrete microstructure and the primary pathway for aggressive agents ingress. Understanding the ITZ is critical to understanding why supplementary cementitious materials improve durability. They densify this zone through pozzolanic reactions. So, before we discuss the individual mechanism, let me give you the landscape. There are six major categories of concrete deterioration. Think of them in two groups. The first three, I mean alkali corrosion, freezing and thawing, and sulfate effect. They are primarily mechanical in their end result. They cause expansion, cracking, and loss of structural integrity from within. The second three, chloride-induced corrosion, carbonation, and abrasion, involve either attack on the reinforcement or surface degradation. In practice, these mechanisms rarely act alone. A bridge deck in a cold climate, for instance, might simultaneously experience freeze-thawing cycles, chloride penetration from de-icing salts, and carbonation of the cover concrete. Each mechanism weakens the concrete in ways that accelerate the others. We will cover alkali-silica reaction and freeze-thaw in significant depth and treat the others at a level of detail appropriate for your practice as a structural engineers. So now let's see how ACI deals with these exposure conditions for durable concrete. So let's look at ACI 318 exposure classification system because this is the starting point for any durability design. ACI 318 uses four letters: F for freeze-thaw, S for sulfate, W for water contact, and C for C for corrosion risk, with numerical subclasses from 0, which means not applicable, to 3, which means very severe. I want you to be able to read this table fluently because you will use it in your careers. For freeze-thaw, F0 means no freeze-thaw exposure, so no requirements. F1 is moderate freeze-thaw without continuous moisture, maximum water cement of 0.55 and minimum strength of 28 megapascal. F2 is severe freeze-thaw in a continuously moist condition. Water cement ratio drops to 0.45, strength increases to 31 megapascal, and air entrainment of 4.5 to 7.5% is now required. F3 is the harshest freeze-thaw with de-icing chemicals and demands water cement ratio of 0.4 and 35 megapascal of strength. For sulfate exposure, S1 through S3 escalate from 150 to over 10,000 milligrams of sulfate per kilogram of soil, with corresponding requirements for sulfate-resistant cement and lower water cement ratios. A key principle that Mehta and Montero state explicitly: every 0.05 increase in water cement ratio approximately doubles permeability. So the jump from 0.45 to 0.5 is not trivial. It roughly doubles the rate at which aggressive agents can penetrate. So when you design a concrete mix, you must check every applicable exposure category and apply the most restrictive requirements. Do not pick and choose. Apply all of them simultaneously. Let's discuss the alkali-silica reaction or ASR first. The ASR was first identified and documented by Thomas Stanton in California in 1940. Based on his observation of distress in highway pavements, it took several more decades before the profession fully understood the mechanism and developed reliable prevention strategies. Why does ASR matter so much? Because its symptoms typically appear 5 to 25 years after construction, long after the contractor has been paid and moved on. The characteristic field symptom is what we call map cracking or grazing, a random network of surface cracks that resemble a road map with crack widths that can reach several millimeters in severe cases. You may also see gel exudation, a whitish or yellowish deposit seeping from cracks, and measurable expansion of structural elements. The key constraint for ASR is that it requires all three prerequisites simultaneously. Number one, reactive silica, two, sufficient alkalis, and three, moisture. All three factors must be present and active at the same time. So let's go through the ASR mechanism step by step. Understanding this at a chemical level will help you remember the prevention strategies because each strategy directly targets one or more of these steps. Step 1. Certain aggregates contain reactive silica minerals. The most reactive phases are opal, which is amorphous hydrated silica, jet and flint, volcanic glass, and chalcedony. What makes these phases reactive is their disordered atomic structure. These disordered phases are accessible to chemical attack. Step 2. The pore solution in concrete is highly alkaline. pH, pH typically between 12.5 and 13.5 due to dissolved sodium, potassium, and hydroxyl ions from cement hydration. These hydroxyl ions attack the silicon-oxygen bonds in the reactive silica, breaking it down into smaller soluble units. Step 3. The broken down silica reacts with sodium and potassium ions in the pore solution to form a hydrated alkali silica gel. This gel is amorphous and critically hygroscopic, meaning it has a strong affinity for water. Step 4. When the gel absorbs pore water, it swells. The volumetric expansion generates internal pressure that can exceed the tensile strength of the surrounding cement paste, which is only about 2 to 5 megapascal. This causes the characteristic map cracking we see at surface. It's important to understand that the cracking isn't chemical reaction itself, it's a mechanical consequence of the gel swelling. The reaction can proceed for decades before visible damage appears, which is why early detection is difficult. This slide summarizes what ACA 221 calls the three prerequisites for alkali silica reaction. I like to call it the alkali silica reaction triangle, the ASR triangle. All three corners must be present simultaneously for the reaction to proceed. Target any corner and you can prevent ASR. Corner 1 is reactive silica in the aggregates. Remember, not all aggregates are reactive. Granite, limestone, and well-crystallized quartzite are generally safe. The problematic minerals are those which I mentioned on the previous slide: opal, jet, volcanic glass, obsidian, and the others. One important nuance: certain aggregates may contain only small amounts of reactive silica, but still cause significant expansion. This is called the specimen effect. There is an optimum reactive silica content that causes maximum expansion. Too little causes little reaction, too much dilutes the alkali. Corner 2. Sufficient alkalis. The critical threshold is generally taken as a sodium equivalent alkali content. The equivalent is calculated as sodium dioxide plus 0.658 times calcium oxide. Alkalis can also come from mixed water from de-icing salt penetrating the concrete surface and from seawater. The critical total alkali loading in the concrete mix is generally taken as 3 kg per cubic meter based on work by Hobbs in 1988. Corner 3. Moisture. ASR requires a relative humidity above 80%. In very dry environment, the gel forms but cannot swell because there is no water to absorb. This is why indoor concrete rarely shows ASR. However, once ASR has begun, removing moisture arrests but does not reverse the damage. The gel remains in place and will swell again when moisture returns. Now, how do we test for ASR potential? There are four standard methods you should know, and they each have important practical trade-offs. The first is ASTM C1260, the Accelerated Mortar Bar Test, or AMBT. This is the fastest test. Mortar bar specimens are immersed in a normal sodium hydroxide solution at 80 degrees Celsius for 14 days. The expansion is measured. If expansion exceeds 0.1%, the aggregate is potentially reactive. If it exceeds 0.2%, it is considered very reactive. The main advantage is speed because the results are obtained in 2 weeks. The main disadvantage is conservatism. It can flag aggregates as reactive that would perform perfectly well in real concrete. This is because the aggressive test conditions don't represent in-service conditions. The second is ASTM C1293, the concrete prism test. This is the most reliable method. Concrete prism specimens are stored at 38 degrees Celsius and 100% relative humidity for 1 to 2 years. An expansion exceeding 0.04% at 1 year or 2 years for confirmation indicates potential reactivity. ACI 221 and ASTO prefer this method because it uses actual concrete, not mortar, and uses realistic alkali levels. The advantage, sorry, the disadvantage is obviously the time, 1 to 2 years before a verdict. The third is ASTM C295, petrographic examination. A trained petrographer examines thin sections of the aggregate under polarized light and scanning electron microscopy to directly identify reactive mineral phases. This gives you mineralogical information no chemical test can provide. Its limitation is that it tells you what's there, but not definitely how much expansion will occur. The fourth is ASTM C1567, the modified mortar bar test. This is the same protocol as C1260, but with supplementary cementitious material blended in. It's used to evaluate whether a proposed supplementary cementitious material, for example silica fume fly ash, mitigation strategy is effective for a specific aggregate. or not. It's very useful for mixed design verification. Here is the good news. Alkali silica reaction is entirely preventable. We have 5 proven strategies. The most direct approach is using low alkali cement. ACI 221 recommends this as the most straightforward preventive measure. When this is combined with a low total alkali loading in the mix, the risk drops dramatically. The second and most widely used strategy is supplementary cementitious material replacement. Class F fly ash at 25% replacement or more, ground granulated blast furnace slag at 35% or more, or silica fume at 10% or more, all effectively suppress alkali silica reaction. They work by two mechanisms: diluting the alkali concentration in the pore solution and consuming calcium hydroxide through pozzolanic reactions, which further reduces pore solution pH. The third strategy is lithium admixtures, specifically lithium nitrate or lithium carbonate. These work by altering the chemistry of the ASR gel so that it forms in a non-expansive crystalline form rather than an expansive amorphous form. The fourth and best long-term approach is simply specifying non-reactive aggregates certified by ASTM C33 as non-reactive by C1293 or C1260 testing. This eliminates the problem at source. Finally, moisture control through waterproofing and sealers can slow ASR progression in existing structures, but it cannot stop it once it has begun. It buys time for repair planning. Okay, so we continue our topic of durable concrete. We previously went through the alkali silica reaction. We covered its uh, different testing methods and preventive measures. So let's move to our second major topic, which is about freezing and thawing deterioration. Now, this is the dominant durability concern in cold climates. In Pakistan, it's particularly for structures in northern mountain regions, the Karakoram Highway, the structures in Hindu Kush and Himalaya foothills, and anywhere temperatures cycle through 0 degrees Celsius regularly. The fundamental physical fact that you all need to remember is this: water expands approximately 9% when it freezes. Now, that seems like a small number, but when water is confined within the rigid pore structures of hardened cement paste and has nowhere to go, that 9% expansion generates hydraulic pressure that, according to TC powers, could theoretically reach 200 megapascal in a sealed pore. Concrete's tensile strength is 2 to 5 megapascal. So this is an enormous mismatch. What makes this insidious is the cumulative nature of the damage. Each freeze-thaw cycle may cause only microscopic cracking, but remember, after hundreds of cycles over 5 to 10 winters, those micro cracks propagate and merge, ultimately leading to surface scaling, aggregate exposure, and eventually structural section loss. De-icing salts commonly used on roads and bridge decks make the problem significantly worse. They don't just depress the freezing point, they create additional osmotic pressure effects that attack the concrete surface. So this is why ACI most severe freeze-thaw class F3 specifically includes exposure to de-icing chemicals. And before that, my apologies for this whistling sound. I have tried my best to avoid it, and uh, somehow, somehow this won't go away. Anyway, um, let's continue. So, the step one uh, is that as the temperature drops below 0 degrees Celsius, water in large capillary pores begins to freeze first. Mm, As ice forms, it expands 9%, displacing unfrozen water towards smaller pores and through the paste matrix. Step 2. This displaced water must find somewhere to go. As it moves through the narrow capillary channel, it encounters resistance. That resistance generates hydraulic pressure. And TC Powers showed that this pressure is proportional to the distance the water must travel to reach an escape point. Step 3. If that distance is too great, if there is no nearby air void, the hydraulic pressure builds until it exceeds the local tensile strength of the press, initiating a micro crack. Step 4. With each subsequent freeze-thaw cycle, those micro cracks propagate and widen. Eventually, they reach the surface, causing the characteristic surface scaling we see on pavements and bridge decks. Internally, cracking reduces stiffness and over time can measurably reduce the elastic modulus of concrete. Step 5. De-icing solves compound the damage through an additional osmotic pressure mechanism. When a saline solution is in contact with pure ice or dilute solution in the concrete pores, osmotic pressure drives water movement. This movement generally is towards the higher concentration gradient. This adds another layer of internal stress on top of the hydraulic pressure. So the key insight from Power's analysis is that, and the design solution is that if we create closely spaced air voids throughout the paste, we give the displaced water somewhere to go, relieving the pressure before it reaches the tensile strength of concrete. That is the exceptional physical mechanism behind air entrainment, which we will cover next. The American Concrete Institute ACI 31819 defines four freeze-thaw exposure classes designated as F0, F1, F2 and F3. Now let me walk through each one so you can apply them correctly in design. F0 is assigned to concrete not exposed to freezing and thawing in a moist condition. Think interior slabs on grade, footings in frost-free zones, or protected interior elements. No special freeze-thaw requirements apply here. F1 covers moderate freeze-thaw exposures where the concrete will not be continuously moist. A covered exterior element or a wall that dries out between wet seasons might qualify. Maximum water cement ratio here is 0.55, minimum strength is 28 megapascal. Air entrainment isn't required by ACI 318 for this class, though it's a good practice. F2 applies to concrete exposed to repeated freeze-thaw cycles in a continuously moist condition. This is the category for outdoor exposed slabs, retaining walls and bridge elements not exposed to de-icing chemicals. Now requirement tightens significantly. Water cement ratio drops to 0.45. Minimum strength is 31 megapascal, and you must specify entrant air of 4.5 to 7.5%. F3 is the most severe continuous freeze-thaw exposure plus de-icing chemicals. This is typical of road pavement, parking garage decks, and bridge abutments. Requirements are strict here. Water cement ratio of 0.45, minimum 35 megapascal of strength, and the same air entrainment range of 4.5 to 7.5% applies here. One thing I want to emphasize here is that these are minimum requirements. Uh, a high traffic bridge deck in a severe climate might uh, meet higher requirements. So please note that these minimum requirements, they set the floor, not the ceiling. Okay, so now since we know what freezing and thawing can do to concrete, let's discuss what's the best defense mechanism that we have got. Now, according to ACI Committee 212 and TC Powers, air entrainment is the single most effective technology we have for protecting concrete against freeze-thaw damage. Let me make sure you understand both the physics and practical requirements. So how does it work? The air entraining administers stabilize tiny air bubbles in the fresh concrete during mixing. These bubbles survive into the hardened concrete as discrete spherical voids 50 micrometer to 1.25 millimeters in diameter. When freezing occurs and hydraulic pressure builds, the nearby air voids act as relief chambers. The displaced water flows into them rather than generating destructive pressure. The system works as long as no capillary pore is more than about 0.1 to 0.2 millimeters from the nearest air void. This geometric requirement is quantified by the spacing factor measured by ASTM C457 microscopy on polished sections of hardened concrete. ACI requires a spacing factor of 0.2 millimeters or less for freeze-thaw resistant concrete. The required total air content from ACI table 19.3.3.1 ranges from about 4.5 to 9% depending on aggregate size. For 19 millimeter maximum aggregate, the F2 and F3 requirements is 5 to 8%. Now a few critical practical points. First, air content drops 1 to 2% during transport and pumping. This is well documented in ACI 212. So you need to specify and bake slightly above minimum and verify air content at the point of placement, not at the truck drum. Second, and this is very important on site, each 1% drop in air content costs approximately 5% of compressive strength. So there is a direct strength air trade-off. This is accounted for in mix design by targeting a slightly higher water cement pressure if needed, but never at the expense of dropping below the minimum air requirement. Third, never allow over-finishing of air-entrained concrete. ACI 302 is very clear on this. Excessive troubling of the surface literally destroys the near-surface air void system, leaving you with a dense surface skin above a properly air-entrained interior. This surface skin is then then highly susceptible to scaling in the first winter. Okay, so we have covered the freezing in time and alkali silica reaction in depth. The other threats to the durable concrete are, for example, the sulfate attack, abrasion, the temperature, fire, and the carbonation and fluoride-induced corrosion of steel. So perhaps this is uh, the last topic which I will be covering in depth, that is the sulfate attack. And for the rest of the threats on durable concrete, I wanted to go through the contents and because uh, your course content basically mentions that we have to cover alkali silica reaction in depth. However, I have covered the freezing and time and sulfate attack as well. So I don't see the reason why should I be covering the other topics in depth. So I leave those topics for you if you are interested. You can go through the contents and check for yourself. I have mentioned also the resources from which you can basically collect the additional information or the knowledge about these topics. So let's discuss the sulfate attack. Now, the sulfate attack is a common problem in structures in contact with sulfate during soil or groundwater conditions you will encounter frequently in various regions of Pakistan. Let me walk through the mechanism and the SEI design requirement. The primary mechanism involves sulfate ions from the soil or groundwater diffusing into the concrete and reacting with two components of hardened cement paste. The first reaction is with the aluminate phases and the second reaction is with calcium hydroxide. Now, the first reaction, which is with aluminate phases, is specifically with tricalcium aluminate and its hydration products. Sulfate ions combine with calcium aluminate to form ethangite. Uh, the critical point here is the enormous volume increase. Ethangite formation involves approximately a 227% expansion. This expansion generates internal stresses that crack and disintegrate the paste. The second reaction is, as I said earlier, is with calcium hydroxide that forms during cement hydration to produce gypsum. Gypsum formation softens the paste, causing it to lose cohesion and crumble. There is also a third, less common form called thomsite attack, and this occurs at low temperature, typically below 15 degrees Celsius, and uniquely attacks calcium silicate hydrate gel itself. Now, the ACI code classifies sulfate exposure in four classes from S0 to S3 based on sulfate concentration in soil or water. For S2 and S3 exposure, you must use ASTM type 5 sulfate resistant cement, which basically limits tricalcium aluminate content to 5% or less, combined with the water cement ratio of 0.45 or 0.4 respectively. Adding 30 to 50% F fly ash or slag provides additional resistance by consuming the calcium hydroxide that sulfate needs to react with. Let's discuss the other threat to a durable concrete, which is chloride-induced corrosion of reinforcement. Now, the chloride-induced corrosion of steel reinforcement is the most economically costly form of concrete deterioration worldwide. which is responsible for the majority of bridge rehabilitation expenditures globally. The corrosion model divides the chloride-induced corrosion process into two phases: the initiation phase and the propagation phase. For initiation phase, chloride ions diffuse through the concrete cover from the external environment, seawater spray, de-icing salt, or coastal atmosphere towards the embedded steel. The concrete provides a passive alkaline environment that normally protects the steel. Fresh hydrated paste has a pH of 12.5 to 13.5, which maintains a stable protective oxide film on the steel surface. The initiation phase ends when the chloride concentration at the steel surface exceeds a critical threshold. The ACI 318 sets this threshold at 0.2% chloride by weight of cement for structures in moist conditions exposed to external chloride. The propagation phase. Once the threshold is exceeded, the passive oxide layer breaks down locally and active corrosion begins. Iron oxides to ferrous oxides and then to hydrated iron oxide, which is the rust. For the design engineer, ACI code requires maximum water cement ratio of 0.4 for C2 exposure, minimum cover of 38 to 75 mm depending on member type, and permits the use of epoxy coated rebar, stainless steel rebar, or calcium nitrate corrosion inhibitors as supplementary measures. Silica film is particularly effective at reducing the chloride diffusion coefficient by 2 to 5 times compared to plain concrete because it dramatically densifies the ITZ, which is interfacial transition zone. So I will be briefly covering this slide, which is about the carbonation of concrete. Remember that carbonation is a chemical process that progressively reduces the pH of concrete over time, ultimately leading to, uh, to the onset of corrosion. It's slower than chloride attack in most cases, but it's relevant to virtually every outdoor concrete structure. So, from a design standpoint, the main defenses against carbonation of concrete are basically the lower water cement ratio, uh, good concrete cover, and proper curing. Remember that carbonation depth can be measured in the field using phenolphthalein indicator, a pH indicator solution that turns things above pH 9. Let me briefly cover three additional durability threats that are important in a specific application. Abrasion affects industrial floors, pavements, and hydraulic structures. It's caused by traffic loading, vehicle tires on pavements, foot traffic on floors, and by solid particles suspended in flowing water. Abrasion resistance correlates strongly with compressive strength. SAI Committee 330 recommends a minimum strength of 35 MPa for parking structures and at least that for industrial floors. Hard aggregates, low water cement ratio, and proper curing all improve abrasion resistance. You can evaluate it using ASTM C779, the revolving disc apparatus test. The second one is cavitation and erosion. Remember, cavitation is a related but more severe form of erosion that occurs in high velocity hydraulic structures, dam spillways, outlet works, and pipelines. So, when water velocity exceeds about 12 meters per second, local pressure drops can cause vapor bubbles to form. When these bubbles collapse near the concrete surface, they generate localized shock waves that can remove concrete at an extraordinary rate. The only practical solution is geometric design to avoid flow separation combined with very high strength, very low permeability concrete, often incorporating silica film. And the ACI 210 covers hydraulic structures specifically, so if you are interested, you can go through the committee's report. And now finally, the resistance and thermal effect. Remember that concrete generally behaves well in fire. It's non-combustible and has low thermal conductivity, but at high temperature, the strength of concrete degrades significantly. For example, at 300 degrees Celsius, you can lose about 15% of concrete strength. At 600 degrees Celsius, losses of 50 to 80% are typical. Siliceous aggregates, particularly quartz, undergo a mineralogical transformation at 573 degrees Celsius that causes additional damage. The limestone aggregates retain the strength better at elevated temperatures. Then the final point is that if you are using fibers, for example, propylene fibers, polypropylene fibers, they melt at about 165 degrees Celsius. They so by melting, they create micro channels which release steam pressure during the fire and dramatically reduce the explosive spalling. So with that, we have covered the majority of threats which affect the concrete durability. So in our upcoming session, we shall be covering what are the means which can be used to improve the concrete durability. For example, the mix design, the curing, the concrete cover. So we shall be covering those in upcoming session in depth. Okay, so we have covered now the different threats to the durability of concrete. So let's discuss some of the means which can be employed or used for improving the durability. And the first one is basically the supplementary cementitious material. Uh, what we call them is basically the SCM. Now, the supplementary cementitious material are probably the single most powerful tool we have for improving concrete durability. Let me cover the three most important ones. The first one is fly ash. Remember, fly ash is a byproduct of coal combustion, classified under ASTM C618. Class F fly ash produced from anthracite or bituminous coal has high silica and alumina content and is strongly pozzolanic. It reacts with calcium hydroxide released during cement hydration to form additional calcium silicate hydrate gas. Class C fly ash from subbituminous coal has more calcium and is both pozzolanic and slightly hydraulic, whereas Class F is strongly preferred for durability because Class C can itself contribute alkalis relevant to ASR. ACI guidelines call for 20 to 40% replacement by cement mass. For alkali-silica reaction mitigation, ACI 221 specifies 25% minimum of class F. Now, ground granulated blast furnace slag or GGBS. Uh, it is a latent hydraulic material, meaning it doesn't react significantly with water alone, but activates in the presence of calcium hydroxide released by cement hydration. It's classified under ASTM C989 in grades 80, 100, and 120, with grade 120 having the highest reactivity. So, uh, replacement levels of 35 to 65% are typical, and GGBS dramatically, remember, reduces the chloride diffusion coefficient. I mean by 2 to 5 times. making it an excellent choice for marine and de-icing salt environments. Now, the silica fume. Silica fume is basically the ultrafine byproduct of silicon and ferrosilicon alloy production. It's classified under ASTM C1240. It's 90 to 98% amorphous silica with an extremely high surface area, typically 15,000 to 25,000 square meters per kilogram versus 300 to 400 for Portland cement. Even at 5 to 15% replacement, it fills the capillary pores and dramatically densifies the ITG. Remember, ITG is the interfacial transition zone, which is the weakest link in the cement matrix. So it reduces permeability to levels where even rapid chloride permeability test registers in the very low or negligible category. I mean below 1000 coulombs. ACA 221 requires only 10% minimum for ASR mitigation. The trade-off is high water demand requirement. So you need to use the higher range water reducing admixtures to maintain the workability. The second approach for durability of concrete is that you design your concrete mix in such a way that it results in a durable concrete. So now let's bring together what we have learned into the mix design process. ACA 211 provides the standard procedure, but for durability focused design, remember that there are 8 sequential steps which you need to follow. Step 1, determine the exposure class. So before you do any strength calculation, classify the structure using ACI 318 19 table 19.3.1. What is the freeze-thaw category? How much is the sulfate content and the chloride, etc. Every structure may have multiple applicable categories. Step 2, establish the maximum water to cementitious material ratio. From ACA 31819 table 19.3.3.1, read off the most restrictive, that is the lowest water cement limit across all applicable exposure classes. So this is your upper bound, you cannot exceed it. Step 3, determine the minimum compressive strength. ACA 318 pairs its water cement limit with minimum strength class. However, the design strength for a structural purpose may be higher, and you must then also apply the standard over design margin from table 26.4.3.1. Step 4, select air content. If any freeze thaw exposure applies, specify entrant air per table 19.3.3.1 based on your nominal maximum aggregate size. Step 5, select slump. The workability target from table 6.3.1 of ACI 211. Then always use a high range water reducer to achieve the required workability without increasing the water cement pressure. Step 6, select maximum aggregate size. So you can uh, take the guidance from three provisions. Uh, First one, for example, is that uh, the farm, the aggregate size basically should be one-fifth of the farm width. The second provision is that the aggregate size should be less than one-third of the slab depth. And the third provision is that the aggregate size should be three-quarters of the clear bar spacing. So all these limits are specified in ACI 211. Step 7 is specify the supplementary cementitious material based on the exposure conditions. Select that type and replacement level which basically satisfy the alkali silica reaction sulfate or chloride requirements simultaneously. Step 8 is trial batches. Test air content, slump and strength. For critical durability application, also test chloride permeability by STM C1202. A result below 1000 coulombs at 28 days indicate very low permeability. I have covered concrete cover briefly in my previous sessions. So remember, it's your first and most important physical barrier against corrosion. So concrete, as you know, that concrete cover is the thickness of concrete between the outer surface and the nearest edge of the embedded reinforcement. So getting the cover right on site is as important as getting the mixed design right. And it's often where most of the projects in Pakistan fail. So ACI 31819 section 26.1.3 specifies minimum cover requirements. Let me highlight the key values here for you. For concrete cast against permanently in contact with earth, like footings, the minimum cover is 75 millimeter. This is generous because the formwork is typically the soil itself. For concrete exposed to weather, like exterior walls and beams, the cover depends on bar size. For bars number 19 to number 57, the minimum is 50 millimeter. For smaller bars, it's 38 millimeter. For interior slabs, walls, and joists not exposed to weather, cover can be reduced to as little as 19 millimeter for smaller bars and 38 millimeter for the largest bars. For beam and column primary reinforcement, the standard minimum is 38 millimeter. For marine or severe corrosion environment, 50 to 75 millimeter is recommended with the higher value appropriate for directly submerged elements. Now, achieving a specified cover on site requires active management. So you need plastic bar chairs, not bricks, wood chips, or rebar fragments, which are common on local sites and cause serious problems. You need to verify cover with an electromagnetic cover meter before, during, and after concrete placement. Now, regarding curing, remember that we have covered curing and compaction in detail while we were having the physical classes. So here I will only be basically uh, touching only the key points which are important with regard to the durability of concrete. So kindly go through the definition and different means or methods through which the curing can be done. I am only going to discuss only those points which are important with respect to durability of the concrete. So why is it so important? Remember, at the molecular level, Cement hydration is a chemical reaction that requires water. If the concrete surface dries out prematurely, hydration stops in the near surface zone. The result is large capillary pores, and we have already established that large capillary pores means high permeability and poor durability. Research cited by Mehta and Montero shows that adequate curing can increase strength by 25 to 50% and reduce permeability by 50 to 80% compared to no curing. These are not marginal improvements. Now, for winter concreting, remember ACA 306 requires maintaining concrete temperature at 10 degrees Celsius or higher during curing. The minimum temperature for adequate hydration rate, remember, is the 10 degrees Celsius for winters. For hot weather, ACI 305 limits fresh concrete temperature to 35 degrees Celsius. Now, one final point in this slide is that if you are using fly ash or slag as supplementary cementitious material, the curing duration should be extended by 1.5 times the standard period because these materials hydrate more slowly than Portland cement alone. And now, as practicing engineers, you will need to specify and interpret durability tests. Let me walk you through the six most important ASTM standards. The ASTM C1202, the rapid chloride permeability test, is probably the most widely used acceptance test for chloride resistance. A 50 mm thick slice of concrete is subjected to 60 volts DC for 6 hours. The total charge passed in coulombs indicates the permeability level. Below 1000 coulombs is very low, 1 to 2000 is low, and below 4000 is high. Now ACA 318 specifies 1500 coulombs maximum for marine exposure. Be aware that this test is an electric conductivity measurement, not a direct transport measurement. STMC 642 absorption and voids is a simple low-cost test. The specimen is dried, weighed, then saturated with water. The total absorbed water gives you the volume of permeable voids. Below 5% is considered low permeability, very useful for ongoing quality control. ASTM C1260 and C1293 for alkali-silica reaction, we have already covered these in detail, so I am skipping these here. Now, ASTM C666 is the freeze-thaw test. Specimens undergo 300 cycles of freezing and thawing while submerged in water. The durability factor is calculated from the relative dynamic modulus measured by resonance frequency testing. Durability factor above 60% after 300 cycles is required by ACI 318 for satisfactory freeze-thaw performance. Finally, ASTM C457 air void analysis on hardened concrete. A polished section is examined microscopically using the linear traverse method. This gives you air content, bubble diameter distribution, a specific surface, and most importantly, the spacing factor. If your spacing factor exceeds 0.2 mm, your air entrant concrete will not perform adequately in freeze-thaw conditions. The construction quality control for durability. Remember, even the best mix design fails if not executed properly on site. Let me go through the six key construction control points. First one is batching and mixing, second transport and placement, third vibration, fourth finishing, and then the remaining cold and hot weather and etc. So I shall be discussing with you these in detail. First one is the batching and mixing. Remember, ACI Committee 305 requires batching by mass, not by volume. Volume batching introduces variability that undermines your durability design. The water cement ratio must not deviate by more than 0.03 from the design value. Also, verify admixture compatibility in advance because some combinations of supplementary cementitious material and admixtures can cause unexpected setting time changes. Now regarding transport and placement, ASTM C94 limits the time from batching to concrete discharge to 1.5 hours or 300 drum revolutions, whichever comes first. Concrete temperature during placement should be between 10 to 32 degree Celsius. Also, avoid free fall drops greater than 1.5 meter to prevent segregation of the concrete. Vibration ACI 309 covers consolidation in detail. We also have discussed this in depth. So I leave this for you. Regarding finishing, this one is critical for air entrant concrete. ACI 302 is very clear. Do not use a steel trowel on air entrant slabs. Do not finish while bleed water is present on the surface. Never sprinkle dry cement on the surface to absorb bleed water. This creates a zone of extremely high water cement at the very surface, which will scale within the first winter. Now, cold and hot weather. ACI 306 for cold, ACI 305 for hot. Maintain concrete temperature at a minimum of 10 degrees Celsius during placement and curing. In hot weather, use chilled water, crushed ice, or liquid nitrogen injection to control fresh concrete temperature. Regarding inspection, you can use electromagnetic cover meters to verify the rebar cover before and after pour. Concrete testing for STM C42 except at 85% of specified strength for course. For high stakes projects, specify uh, rapid uh, chloride permeability test for C1202 as a lot acceptance test. So in this slide, I want to address a misconception that I see frequently among both students and practitioners. High strength or high compressive strength is not the same as high durability. Let me be very direct about this. Mehta and Montero state explicitly that a high strength concrete with poor curing or excessive water cement ratio will be less durable than a lower strength well cured low water cement ratio concrete. This isn't a theoretical observation, it's supported by abundant field evidence. The classic example is air entrainment. We know that each 1% of entrained air reduces compressive strength by approximately 5%. If you had a purely strength focused mentality, you might be tempted to reduce air content to boost strength, but doing so would sacrifice freeze-thaw resistance, which is a far more critical durability concern for an exposed element in a cold climate. Similarly, fly ash and slag reduce early strength gain. If the only acceptance criteria on your project is 28 days compressive strength, You might be pressured to reduce supplementary cementitious material content to hit the strength target, but you would be sacrificing long-term permeability resistance, sulfate resistance, and alkali silica reaction mitigation. So the solution is to specify durability requirement explicitly in contract documents. ACA 301 provides a standard specification language for this. So specify maximum water cement ratio, minimum cover, minimum air content, minimum curing duration. So these parameters control durability far more directly than compressive strength alone. This slide is your reference sheet for the ACI documents that we have referenced throughout our discussion on concrete durability. I recommend you bookmark this slide and use it when you are writing project specifications or reviewing existing ones. If you want to dive further or dig deeper, here is the list of key reference documents and the textbook, so you can go through them. I recommend that you go through all these reference documents wherever you have basically the question or any ambiguity. Now let's close with the six most important things I want you to remember. First, durability is a design choice. It doesn't happen by default. You must engineer it explicitly through every decision: mix design, material selection, cover, curing, and construction practice. Second, for alkali silica reaction, remember the triangle. You need all three corners simultaneously: reactive silica, sufficient alkalis, and moisture. Your prevention strategy should target at least one corner, and using supplementary cementitious material is usually the most cost-effective and reliable approach. Third, air entrainment is non-negotiable for freeze-thaw exposure. For F2 and F3 conditions, a properly distributed void system, a spacing factor 8 or below 0.2, is the single most effective protection measure. You cannot substitute higher strength or lower water cement ratio for air entrainment. Fourth, supplementary cementitious material like fly ash, silica fume are multi-purpose. So fly ash, GGBS, and silica fume simultaneously improve workability, reduce permeability, mitigate ASR and sulfate attack, and enhance long-term strength. They represent excellent value in any durability critical project. Fifth, permeability governs almost every durability problem is at root a transport problem. Control the water cement ratio, cure properly, and use dense paste, and you address the root cause of most deterioration mechanisms at once. Sixth, ACI 201, 221, and 318 are your baseline. Never design below these standards. Always specify durability requirements, not just compressive strength. So, when you only specify compressive strength in your contract document, then strength alone is a poor proxy for durability. As engineers, you are responsible for the structures you design. They will serve communities for 50 to 100 years or fail prematurely at great cost. Durable concrete is sustainable concrete, and sustainable concrete is responsible engineering. Thank you.